everyone, welcome to the lecture again. Today we are going to start the discussion on moment of inertia. In this lecture we will discuss the moment of inertia of standard bodies and the parallel axis theorem, the perpendicular axis theorem and the radius of gyration. So, let us see what is moment of inertia. Let us say I have a rigid body and that rigid body is rotating about an axis with an angular acceleration of alpha. So, let us say this is O prime and the mass of this rigid body is m. Then as I said, this body or a rigid body of mass m is rotating about O prime with angular acceleration alpha. Okay. Now, let us consider a small mass dm, okay, which is at a distance, let us say r away. So, the tangential acceleration, because it is rotating, so this mass is going to have a tangential acceleration, and we know in planar polar coordinate the acceleration a is minus r theta dot square r cap plus r theta double dot theta cap. This theta double dot is the angular acceleration which is alpha here. So, therefore, for mass dm, the component of tangential acceleration or the acceleration which is tangent to its circular path, because this mass dm is going in a circular path. So, circular path is, so the acceleration or the tangential acceleration is r times theta double dot, which is alpha here. Okay. Now, let us calculate the force on this mass dm. So, therefore, the resultant tangential force or the tangent force on the element dm is force equal to mass time acceleration. So, r alpha times dm. Okay. Now, let us calculate the torque that is acting on the mass dm or the moment of this force. So, the moment of this force, which is also called torque, is equal to, so we have to take the moment of this, so we have to multiply this by r. So, it becomes r square alpha dm. Okay. Now, this moment or the torque is for the small element dm. For the entire body, for the body, the rigid body that we have, it will be integral r square alpha dm. Now, note that because it is the rigid body, so every point on the rigid body is moving with the same angular acceleration alpha. Therefore, this alpha is independent of the integral and I can take it outside. Okay. So, let me mention this. For the rigid body, this alpha is same, therefore, it can be taken outside the integral and we can write down the moment for the body, let me denote it by tau equal to alpha integral r square dm. Let me define this quantity r square dm as a moment of inertia I. So, tau becomes I times alpha. Okay. Let me call it equation number 1. Here note that the I is integral r square dm. Let me compare it with F equal to ma. Okay. So, this is the famous Newton's law. Let us compare 1 and 2, and just by comparison we can make the following statement: just as the mass m of a body is a measure of the resistance to the translational acceleration, the moment of inertia I is the measure of the resistance to rotational acceleration of the body. From equation number 2, you can see that the mass m is the measure of the resistance to the translational acceleration A. Similarly, the moment of inertia I is the resistance of the rotational acceleration alpha of the body. So, this is the physical significance. Let us look at moment of inertia I. Let us say I have a rigid body, and this rigid body has a mass m, and it is rotating about o prime. Then the moment of inertia of a rigid body of mass m about an axis, say o prime, is defined as I equal to integral r square dm. So, we take a small mass dm at a distance r, and then you find out this integral. Now, based on this, let us look at the moment of inertia of some standard object. Okay. So, first let us look at the moment of inertia of a rod. Moment of inertia of a, let us say, a uniform rod of length L and mass m about an axis through the middle point and perpendicular to it. So, we have the following situation: we have this rod, and the mass of the rod is m, the length is L, and let us say we want to find out the moment of inertia about an axis which passes through the middle point and that is perpendicular to it. So, this is our o prime. Okay. So, to find out the moment of inertia, let us consider a small mass dm at a distance of x. So, the mass is dm and this length is dx. Okay. So, dm, the mass will be the mass per unit length multiplied by dx. So, mass per unit length is m by L into dx. This is my dm. Now, the moment of inertia will be integral x square and dm. So, dm is m by L dx. Okay. So, here m by L I can take outside and the integral of x square is x to the power 3 divided by 3 and the limit are from minus L by 2 to plus L by 2. So, this point is minus L by 2 and that point is plus L by 2. So, it is minus L by 2 to plus L by 2. So, therefore, it is m over 3L, L to the power 3 divided by 8 plus L to the power 3 divided by 8 and that comes out to be m L square divided by 12. This is the moment of inertia of a rod of length L, mass m about an axis which is perpendicular to the rod and it passes through the middle point. Now, let us look at the moment of inertia of a circular ring. Okay. In the first case, let us say about diameter and then let us consider about an axis through the center and perpendicular to its plane. Okay. So, the first case is about diameter. So, we have a ring and this is the diameter passes through the center O. Let us say this point is A prime and A. So, we want to calculate the moment of inertia about A prime. Now, to find out the moment of inertia I need dm. Dm will be the mass per unit length. So, m over 2 pi a where a is the radius of this ring and multiplied by the infinitesimal length. So, let us say this is a, this angle is theta. So, therefore, this is d theta and that length will be a d theta. So, multiplied by a d theta. This is the mass of this small part dm. Now, the moment of inertia will be integral r square dm. So, we want to calculate the moment of inertia about this axis. So, we have to see how far this mass is from this axis. Okay. Now, from the geometry you can see that since this length is a, this angle is theta, therefore, this length will be a sin theta. So, we will have a sin theta square dm is m over 2 pi a into a d theta. Now, the limit of theta you can clearly see that theta varies from 0 to 2 pi. Okay. So, this comes out to be m and a square, this a will get cancelled with that a. So, m a square over 2 pi 0 to 2 pi sin square theta d theta and this comes out to be half m a square. So, this is the moment of inertia of the circular ring about the diameter. Now, let us consider the second case, the moment of inertia about the axis which is passing through the center and perpendicular to its plane. So, we have this ring and the moment of inertia about let us say this axis. Okay. So, in this case again the dm will be the same. So, dm will be m over 2 pi a into a d theta, but the distance r from this is going to be fixed and it is going to be a only. So, it does not matter whether you are here or there, from this axis the distance is always a. So, therefore, the moment of inertia will be a square dm, m over 2 pi a into a d theta, and the limit is from 0 to 2 pi. So, let me take the constant outside, this a will get cancelled with that a. So, we have m a square over 2 pi 0 to 2 pi d theta, which is m a square over 2 pi into 2 pi, that is equal to m a square. Okay. Similarly, the moment of inertia of other standard object can be calculated. Now, I am not calculating it, but I am writing down the end results. So, let us say a thin rectangular plate, okay. So, let us say I have the x axis, the y axis and the z axis, okay, and we want to calculate the moment of inertia about a point that is passes through the center and which is perpendicular to the plane of the rectangular plate. So, in this case I z, so let us say this is z axis will be m divided by 12 a square plus b square. Okay. If you have a thin circular disc, okay, so this is a disc and the moment of inertia again about a axis which is passing through the center and perpendicular to the plane will be half m r square, where r is the radius of it, and this moment of inertia I have written, let us say about z prime. Okay. Now, if you have a sphere, then the moment of inertia about the center is 2 by 5 m r square. For spherical cell, the moment of inertia is 2 by 3 m r square. So, all of them you can calculate using this relation I equal to integral r square dm. Okay. Now, for the cylinder, so let us say I have a cylinder of, let us say height is h and the radius is r, and let us say this is o prime, okay. Then the moment of inertia about o prime, okay. So, let me also call it z axis will be half m r square, okay. And if you calculate the moment of inertia about the x or y axis, so let us say this is your x axis and this is your y axis, then it is about x and y axis it will be the same, and I x equal to I y equal to m divided by 12 3 r square plus h square, okay. So, small r or capital R they are same here, okay. Now, let us look at the moment of inertia of an elliptic disc. Okay. So, let us say we have a elliptic disc, its semi major axis is A and semi minor axis is B, then the moment of inertia about major axis will be 1 by 4 m b square, and about the minor axis it will be 1 by 4 m a square. Okay. And note that the equation of the ellipse is x square over a square plus y square over b square equal to 1. Now, the moment of inertia of a rectangular prism or sometimes it is also called parallel pipette okay. So, we have this parallel pipette, its let us say length is A, B and C. Okay, let us say this is x axis, y axis and z axis. Then the moment of inertia I about x axis. So, about this x let us say it will be m over 12 b square plus c square, I y will be m over 12 c square plus a square, and I z will be m divided by 12 a square plus b square. Okay. Now, let me define the radius of gyration. Okay. So, first let me write down the definition. The radius of gyration, it is denoted by k, of a body about the axis of rotation is defined as the radial distance okay, at which the entire mass of the body should be concentrated if its moment of inertia about the axis is to remain unchanged. Okay. So, for example, let us say I have this rigid body and it has some axis of rotation, and let us say the mass is m. Now, you find out what is the moment of inertia. Let us say the moment of inertia is whatever it is I. Then what you do is you take this mass and keep it at a distance, let us say k, which is the radius of gyration. So, the entire mass is kept at this distance. Okay. Then we put I equal to the moment of inertia of this system is m k square. Okay. So, therefore, this k becomes a square root I over m. Okay. So, you take this body, it has a mass, it has a moment of inertia, take this mass at a distance of k, calculate the moment of inertia and then put it back equal to I. So, whatever distance you get, that is the radius of gyration. Let us understand it by an example, so that it will be clear. So, radius of gyration of a cylinder, let us say about its central axis. Okay. So, we have a cylinder and this is the central axis, let us say OO prime. Then we know the moment of inertia about OO prime is half m r square. So, this is your I, this you put equal to m k square. Okay. So, let me put your I, which is half m r square equal to m k square. Okay. Then k is the radius of gyration. Let us find out what is k. So, k is r over square root 2. Okay. Let us look at another example. Let us say radius of gyration of solid sphere, okay, about a diameter. So, the moment of inertia of a solid sphere is 2 by 5 m r square. Let us put this equal to m k square. So, m will get cancelled. So, from here k comes out to be square root 2 divided by 5 into r. Okay. Now, let us look at the parallel axis theorem. Okay. Let us say I have a rigid body, okay, and we have an axis that is passing through the center of mass. Let me call it B prime, and you want to calculate what is the moment of inertia of this body about an axis which is parallel to it. So, let us say it is situated at a distance of d. So, this is A prime. Then the moment of inertia about A prime, let me denote it by I, equal to the moment of inertia about B prime, let me denote it by I bar, plus m d square. Okay. So, here this I is the moment of inertia about parallel axis at a distance d, and I bar is the moment of inertia about the central axis. Okay. So, here it is B prime. Okay. Let us prove this statement. Okay. So, we have this rigid body and we have the axis which is passing through the center of mass, which is G here, and we want to calculate. So, this was our B prime, and we want to calculate the moment of inertia about A prime. Okay. So, the moment of inertia about A prime will be, so let us take a small mass dm, okay, and let us say this mass dm is at a distance of r. Okay. So, this is the perpendicular distance, okay, because this object is in 3D. So, I equal to integral r square dm. Okay. Now, this A prime axis is situated at a distance of d. So, this distance is d, okay, and let us say from G the mass dm is at a distance of r naught. Okay. Then I can write this down as integral d plus r naught square dm, because r is d plus r naught, and let us say this r naught is making an angle theta, okay, from the horizontal line, and this distance is, let us say, u. Okay. In that case, so for this geometry I can write down this as d square plus r naught square plus 2 d r naught cos theta into dm, okay, or I can write this down as d square dm plus integral r naught square dm plus 2 d into r naught cos theta is nothing but u, okay. So, 2u dm, because from the geometry r naught cos theta is equal to u. So, this integral r naught square dm is the moment of inertia of this rigid body about b prime, okay. So, let me write it as I bar. So, I have I equal to I bar plus this d is constant, okay. So, I can take d square outside and integral dm is the total mass. So, it becomes m d square. Now, look at here, 2 and d is constant, okay. So, that I can take outside. So, this I can rewrite as 2d integral u dm, okay. But since this x is b prime b is passing through the center of mass. So, therefore, integral u dm will be 0, because it is the definition of the center of mass axis. If you take r into dm and then you integrate it, it has to be 0, okay. The reason is u is measured from the axis which is passing through the center of mass, okay, passing through G, okay, and it is the first moment. So, therefore, it has to be 0, okay. So, we got I equal to I bar plus m d square. Now, here you have to note that the parallel axis theorem applies only if one of the axis is a central axis, okay, because only then this term will be 0, okay, and then we can use I equal to I bar plus m d square, otherwise we cannot use it. Let us understand it by an example. So, let us say we want to find out the moment of inertia of a rod of length L about an axis which is perpendicular to it and passes through one end. Okay. So, we have this rod and we want to find out the moment of inertia about this axis. Okay. So, it is given that the length of this is L, therefore, this length will be L by 2 and the moment of inertia about this axis will be the moment of inertia about the central axis. So, this one plus m into d square. So, d is L by 2, okay. So, I equal to I bar, just now we saw it was m L square divided by 12 plus m L square divided by 4. So, that comes out to be m L square divided by 3. Okay. Now, let us look at the perpendicular axis theorem. let us say I have a body which is in the xy plane, and let us say this is the z axis. So, the statement is following: the moment of inertia of a 2D body, so here the body is 2 dimensional, about an axis perpendicular to the plane is equal to the sum of the moment of inertia of the body about two mutually perpendicular axes lying in the plane of the body. Okay. So, that means that the moment of inertia about the z axis is equal to Ix plus Iy. Okay. So, again it can be proved very easily, because the moment of inertia about the z axis will be, let us take a small mass dm, and let us say it is at a distance r. So, Iz will be integral r square dm, and this r can be written as in terms of x and y. So, r is square root x square plus y square, therefore, r square is x square plus y square dm, and this I can write as integral x square dm plus integral y square dm, and integral x square dm is the moment of inertia about the x axis, and the integral y square dm is the moment of inertia about the y axis. So, we have Iz equal to Ix plus Iy if the body lies in the xy plane. Let us look at it again by an example. So, let us look at the moment of inertia of a disc about a diameter. Okay. So, we have a disc, okay, and let us say this is x axis, this one is the y axis. Then the question is, what is the moment of inertia about the diameter? So, about let us say x axis. Okay. So, we know that the moment of inertia about Iz is mr square divided by 2, and because of the symmetry, Ix and Iy should be equal. Okay. Therefore, Ix or Iy should be mr square divided by 4, okay, because Ix plus Iy should give you Iz. Let us look at the moment of inertia of ring about the diameter. Okay. So, again about the axis which passes through the center and perpendicular to the plane is m r square in case of the ring, and again Ix and Iy should be equal. Therefore, Ix or Iy should be mr square divided by 2. With this, let me stop here. See you in the next class. Thank you.